Alright, time for another draftphysics.com, debatephysics.com also, but can't find debaters. So, Wikipedia was awful in terms of its capacity to accept any kind of argument regarding what it states as the truth. And we all must believe what the editors say, because the editors are infallible, because they're all little popes, okay? And they're all going to tell us what the truth is. And they're going to do it badly, frankly. All right, and they do it here in the third law. So, as I've pointed out in the previous video, physics, the law, three laws, one. Yeah, right. Yeah, those two were wrong, and this third one, the only catch here is that Newton wrote this kind of poorly, frankly, I would argue. All right, so let's just do it real quick. So this is the interpretation of the Latin Newton wrote. So, to every action there is always a opposed and equal reaction. So obviously I could say to you, a shooting star or something is an action. You see something moving somewhere and it's an action. Well, there's not going to be a reaction to the action until the action hits something. So there's no reaction. It's not really about an action. It's about a change. It's about something interacting. So it's more like for every interaction there is always opposed and equal. So in interactions are original actions where something's standing still and then you make it act in that case. All right. The mutual actions of two bodies upon each other are always equal and directed to contrary parts. So I would say that it's worth drawing it and just pointing out how I think it can be reduced. I think it's fair to Newton to say, okay, yes, we can do a little bit of changing of the what exactly is being stated for a better way of stating it. So I would change it to an understanding. See, we already know all this, nuclear physics stuff. So we know that basically there's this idea of what's happening with a nuclear bomb. Obviously, it's an explosion. Why is it exploding? Well, because the stuff that was in very compact, that is stuff in little tiny nucleuses, became stuff in much bigger space. All right, so there's a huge expansion. So most things that explode, that very thing is happening. The chemistry or whatever you're causing to make the explosion happen is basically taking very small things and they're now covering very large areas. So you're expanding where the electrons are, you're expanding. So the idea would be that the expansion moves in all directions is sort of what Newton's saying. Okay, so you could argue that if something happens, there's an action, nothing's happening, and all of a sudden something happening. Well, what's happening is this expansion, and the expansion is in all directions. Explosions are all in all directions. You can't expand just in one direction. You have to expand in both directions, and the whole point is in all three directions. So that's one way to understand the idea. The other way to understand the idea is that if something has action and something else is dead, all right, something's not moving, and the two things hit each other, okay, well, obviously, like the Newton's cradle, this one has the money, okay, it has $10 worth of movement, and it just gives the movement, the $10 to something else. Now, the truth is it could do it partially, and so in the case of two things moving, or two things that have their own what they're doing thing, this one's going 5 in this direction, this one's going 3 in this direction, you can have an interaction where this one exchanges what it has, this one ends up with 5, and this one ends up with 3. The difference being 2. This one went 2, this one went 2. So you're exchanging equally, okay, between your positions. This one can't give away 2, all right, without this one gaining it, of course. And when this one gives away the 2, well, it's obviously $2 shorter. So it's just, you can think of it as just currency exchanges. Things have a currency. They're going to bang into each other, and they're going to divide up what they have, and they can leave with an equal amount, or they can leave with all kinds of amounts, depending on how rich their contact is, how complete it is, how much time they have to exchange their money. So that's a way I would abbreviate it, or explain it, in terms of, I think, the point Newton's getting to. And clearly it is a conservation, statement. But anyway, we'll get to that part. So back to the All right. Overtly brief paraphrases of the third law, like action equals reaction. So that's the one for like in a gun. Okay, it's an explosion. The explosion goes both ways. The gun gets a hunk. The bullet gets a hunk. And it's all so very, very fast that you can't really count on any reflections or anything else. And even if there are reflections, those imply action and reaction, so it's not going to matter. And the idea is that you're going to get the same energy going both ways. Now, obviously, physics says that the bullet has thousands of joules of energy and the gun only has 2 or 3. So it thinks small things going fast has more energy when they have the same exact momentum. And that's what Newton would say, is that he would look at a gun firing and he would see the same energy going both ways. He wouldn't have any delusion, and I'm just going to say it's a delusion, that physics has, that somehow there's more energy going one way. Newton would just say it's one atom going 1,000 miles an hour is the same as 1,000 atoms going 1 mile an hour. Just like with people, one guy running 50 miles an hour is the same as 5 guys running 10. If you do the momentum thing, you have to obviously have one. you obviously have to change the mass to velocity ratios proportionally. All right, like action reaction might have caused confusion among generations of students. So this is so pompous and arrogant, like they're going to talk to students when frankly these people are in no position to qualify somebody else as inferior or less educated than they are, or more poorly educated. It's just really a lame statement. The action and reaction apply to different bodies. So it applies to what you're creating. So right over here, they have a picture of a rocket, right? You can see that, right? Yeah, they got a picture of a rocket. It's kind of proving the point. The rocket's giving away. And it's a fact that it gave away something. You can see it. Now, clearly, it's not giving it. It doesn't need the ground to react. It doesn't care what the ground does. If it murdered 7 million people, the rocket wouldn't care. It wouldn't have anything to do with its flight. I mean, it doesn't fly further because it incinerated 10 million people. So if I put a bunch of people around the bottom of the rocket and they all burn to death, the rocket doesn't go any faster. It doesn't go any further. So it's irrelevant to the circumstance. Well, I guess you could argue if I did do something where I put like a bunch of dynamite and the fire hits the dynamite and explodes the dynamite, well, that could push the rocket more. But it's also going to push force on the other side more also. It's going to increase the magnitude of the explosion happening on the ground also. So it's just really, the rocket's a good example of the giveaway. The rocket's giving away stuff going that way. And the fact is, it had stuff going both ways before it did that. So before it did that, it had stuff going both ways in its tank. It has a bunch of pressure and has a bunch of atomic force going both ways. What's it doing? It's giving it all the way that way. So clearly it has a real disproportion. It has left over a whole bunch of stuff inside of it going that way, and it doesn't have as much stuff going this way because it shot it all out of the rocket. I'm pointing in the wrong camera, but whatever. So it's another way of looking at it. All right. So it says the action and reaction apply to different bodies. For example, consider a book at rest on a table. So it's really a bad example of action and reaction, right? Who the hell would call that an action? Everybody would sit there and say, oh, that's not an action. Why are we talking about a book on a table? It's a real pitiful example. I mean, compared to a rocket, a book on a table, why don't they put a picture of a book on a table? And everybody can say, I don't think Newton was talking about books on tables. Okay, the Earth's gravity pulls down upon the book. Right. Yes, that happens. And there's a bunch of pressure caused on both the book and the table. Both of them are feeling the pressure. The table's heavier because the book's on it. It can feel the pressure the book's applying to the table. And the book is feeling the pressure of the table pushing back. All right, the reaction to that action is not the support force from the table holding up the book. No, it's not just holding it up, it's replacing its position. It's pushing it back up. So it's not just holding it somewhere, it's pushing it somewhere. The book has to push into the table to cause the table to have more force pushing on its legs. Its legs wouldn't have more force on them if the book didn't push into the table. So even this, they can't even make it reasonable. But the gravitational pull of the book is acting on the Earth. So this idea that the gravitational pull of the book is somehow pushing the table towards it and causing the table to cause the compression is just silly, right? So comparing the gravitational force created by a gigantic Earth to the gravitational force produced by a book is a little bit ridiculous. And only in some, I mean, you have to just think about it in terms of the entire universe, and you'd have to think about the fact that, well, the force that the Earth can affect on the book is tiny because the book is very small, so it can only collect a little bit of the Earth's gravity. It can't collect much of it because it's very small. And the fact is the small book is creating a shadow on a very big Earth, so it can, it can't do much to the Earth because it's so damn small. So the Earth it clearly doesn't move, and clearly the book's gravity is a non-issue in the circumstance because the Earth's gravity is in magnitude is so much more substantial. But anyway, it's just a really poor example, frankly. They should have talked about the rocket. That's a good example of Newton's third law. All right, you have the rocket moving up, and you have a big giant pile of energy flying out the other end of the rocket, right? It doesn't matter what it hits. It's a big giant pile of stuff flying very fast coming out of its butt. That's a very good equal and opposite reaction picture. One action going one way where you have one big thing moving kind of slowly, and the other thing, the other side, you have a bunch of tiny little things moving insanely fast. So it's a perfect description of the whole momentum thing. It's a really good illustration. So instead of talking about that, they talked about a book on a table and said that's action and reaction. Now that's the worst possible example almost. Newton's third law relates to a more fundamental principle, so says them. Okay, I think it relates to the more fundamental principle that all explosions go both ways. Just a fact. All expansions. That's all that's happening in the universe, really, is expansions and contractions. This is how the universe feels, which you might call the wave, is the oscillations that are happening all the time. All the time things are being compressed and then they re-expand, and then they compress and they re-expand. And that's in the movement of electrons, essentially. But anyway, the conservation of momentum. So, see, they say these words, they talk about momentum, and then they'll pervert it all into kinetic energy, as if Newton was talking about kinetic energy, when, of course, he wasn't. Energy was momentum for Newton. The latter remains true even in cases where Newton's statement does not. So why would they even say this, that Newton's statement doesn't work? Of course it works. So even this, where Newton's statement does not, where does this statement fail? For instance, when force fields, whatever those are, I don't know, who believes in force fields or whatever force fields are? You mean like in Star Trek or something? What are you talking about? For instance, when force fields, deflector shields or something, what are you talking about? As well as material bodies carry momentum. So we know force carries momentum. So light is a force, it carries momentum. It's moving the speed of light, it carries momentum, yes. And when momentum is defined properly, so here we are, another big pile of crap rhetoric. All right, as if we can't figure out what momentum is. It's mass times velocity. Mass times velocity. They say there's a proper way to define that, which is, no, it's not mass and velocity. It's 1/2 the mass times the velocity squared. What else are they doing this for? Defined properly. Momentum is defined properly. MV. It's not complicated at all. All right, in quantum mechanics as well. So whatever that means, defined properly in quantum mechanics as well. In Newtonian mechanics. So again, they don't even know what Newtonian mechanics is, in the sense that they're going to butcher it so badly. If the two bodies have momenta, okay, so mv1 and mv2, respectively, then the total momentum of the pair is, yes, that's right, they have a total amount of mass and a total amount of velocity. And the fact is that you can plus and minus it, okay, but you always have to have the same stuff coming out. So whatever mass and velocity you start with, mv, You have to have the same amount leaving whatever you put them into. So if two cars, for example, crash, and I have 150 momentums in one car and I have 50 momentums in the other car, the total momentum is 200. And the fact is, when they collide, I can't let just 100 pop out and say, oh yeah, that was conservation of momentum. No, it wasn't. All right, you got to get the 200 back. All right. You can't destroy momentum. You can't ever get rid of it. You're just stuck with it. It always goes somewhere. It's always in something. All right, P2, and the rate of change is P. So this is just wrong. So I'll just say that. Okay, it's just wrong to think you can actually subtract momentums. That is, two cars can hit each other and do nothing. Now, obviously, we're talking about elastic things, right? So yes, obviously they can crush fenders, but that would all be understandable like rockets. That's just turning big things moving into little things moving. So, no momentum is destroyed. You have to do like if I have a total of 200 momentums, I have 150 going this way and I have 50 going this way, and it doesn't matter what's going this way. It doesn't matter which way it's going. If those two things collide, I have to account for the total amount. So if the two hit each other, there's going to be 200 momenta worth of crushing. And if they're elastic and they won't crush, then I have to have 200 worth of movement afterwards. There has to be 200 worth. All right. By Newton's second law, so this is just their formula. They do this stupid instantaneous momentum. There's no such thing as your instantaneous momentum, so why would, whatever. So you're just saying your momentum at a point, a position. Okay, it's always going to be kind of an average, but okay, the momentum at a position. Time is irrelevant. Momentum is not time dependent. Velocity, lots of things are time dependent, but your momentum is already a statement about the quantity of motion you have, which is the energy. You don't need to care about time. It's not about momentum in an amount of time. You don't have a momentum in an amount of time. You have a momentum, which is your total force. It can't be in an amount of time. You can apply it over a time, but it's a total amount of force. So that this fraction is, I would just argue, it's irrational. Putting time under momentum is irrational. It can't do anything but bad things, because your momentum is not time dependent. The amount of joules of energy stored in a piece of dynamite is not time dependent. The amount of water pressure behind, in a dam is not time dependent. I can let the pressure out a little at a time. I can let the pressure out all at once. It's an amount of pressure. It's not time dependent. It's a total amount of pressure. The weight of something, I can pick pieces off of something and make it weigh less. It had a total weight. Now it has less weight. I mean, it's not time dependent. There's no way I can make time change something's momentum. Time can't change its momentum. By Newton's second law, the first term is the total force upon the first body. So the first term is the thing that's equal to this other crap. So what are you even talking about there? But of course it is the total force, but there's no T. There's no time. Time doesn't matter. There's no unit of time for your momentum. I'm just saying it right there. I'm just saying it's just such garbage math. And the second term is the total force upon the second body. So you're saying, again, total force. Then what is the time for? If it's a net force, if it's the total force, who cares how long? Whether it was 1 second or 2 seconds, ain't going to make any difference at all. It doesn't matter. If you're applying the force, it doesn't matter how much time you take to apply it if you're saying what was the total force applied. Just like that rocket thing again, I could cut that thrust into littler pieces, all right, and I'd still have a total amount of total thrust. Now, I obviously couldn't lift the rocket that way because the other forces would consume, the force, because because the velocity does need time. That is time dependent. Okay. I'm going to be fighting more gravity. The whole point of the big giant pile of thrust is to get the thing moving as fast as possible. If I move it slower, then I'm going to be fighting more gravity, and my thrust just gets weaker and weaker. Every extra second, I'm just multiplying how much the ship weighs. I'm making it heavier and heavier the longer I take to get it out of gravity. All right, if the two bodies are isolated from outside influence, the only force upon the first body can be that from the second. So I don't know what this, I don't even know why they write an equation backwards. Do you notice that this equation, can you see this stupid fucking equation? Yes, you can see it. I don't want to have to blow it up. But they have the product here, and then the equal sign, and then these two pieces that add up to it. Now, why the F wouldn't you switch that around and say these two pieces equal the product? Why is it written backwards? Too ridiculous. Anyway. All right. All right. The only force upon the first body can be that from the second, and vice versa. So the fact is they're both independent amounts of momentum, and you must conserve the momentum. So it doesn't matter what direction it's going. It just matters that it's movement. And in the end, you have to have the same amount of mass moving. So if you have 5 pounds of mass moving and 10 pounds of mass moving, and they somehow interact, the end result has to be, in the end, you still have to have exactly the same amount of total momentum. All right, by Newton's third law, these forces have equal magnitude but opposite direction, says them. They can't necessarily have equal magnitude, so right there is a wrong, right? We know that the magnitude of one can be much bigger than the magnitude of the other. I can bang an elephant into a mouse, or I can bang a mouse into an elephant. All right, which one has the force really matters. So they cancel when added. So there's no canceling. So that's just utter rubbish. Nothing ever cancels. It always does this and then does this. Okay, so you can end up back where you started. You can turn your steering wheel right, and then you can turn your steering wheel left. But you can't cancel the motions. You have to actually do one and then do the other. Okay, there's nowhere in physics where anything ever cancels. It's just you undo one action by doing another action. There's no unaction. There's no anti-action. There's no the two actions disappeared. No, the two actions actually have to happen. And they'll place you back where you started, but that doesn't mean nothing happened. That doesn't mean you didn't use twice the amount of energy, right? You used energy to go left, and then you used energy to go right. You didn't cancel the energy. You used the energy. All right, the P is constant. So who can even understand what they're talking about? Yes, obviously the P has to be conserved. It isn't a constant, it's conserved. Alternately, if P is known to be constant, so what are they even talking about? Constant in what case? You're adding two and getting a third product. How could why would you talk about there being any constancy when you're adding two things? Obviously, the third thing can't be the same P. It has to be an addition of the two others. I mean, it doesn't even make sense. It follows that the forces have equal magnitude in opposite direction. So what a mushy pile of incomprehensible drivel. All right. And so this part about candidates for additional laws, and they have some completely doofy word as a Zoroff law, Zeroth law. What the fuck is this? He didn't have no zeroth law. Oh, it just makes you want to throw up. So bad. Okay, examples. So this is it for examples. The study of behavior of massive bodies using Newton's law is known as Newtonian mechanics. Why would they have to be massive? Newton's mechanics covers everything. All mass and all velocity. It doesn't matter how big it is. It doesn't matter how small it is. So again, more mush. Some example problems in Newtonian. So these people are just so caught up in mathematics and being in school or something. That what do you mean example problems? I don't need example problems. I need you to explain actual physical circumstances. To get the concept right. Are particularly noteworthy for conceptual or historical reasons. What is that mush? I mean, just so funny. All right, so uniform accelerated motion. This is all Newtonian law, so yeah, there's nothing to argue there. Okay, this is all fair enough. This is where it goes south. So let's see what they do here to make a mess out of it. So they have the 9.8 meters per second squared, which, where does the square come from? What is it doing there? It's totally unnecessary. The S should be meters per second, period, per 1 second. It's 9.8 meters of velocity. So you denote velocity as meters per a unit of time, an hour, a second, a day. That's how you denote it. So yes, you have to say meters per a unit of time, seconds. And then you're saying, well, how often does the 9.8 happen to you? Well, it happens every 1 second. So they've abbreviated something and then squared the s's because they haven't gone to the bother of writing the actual fraction, which is 9.8 meters per second over 1 second. That's the real ratio. So it's just such junk math. All right, well, I'll read from here. Let's see. All right, where m is the mass of the falling body, big M is the mass of the Earth, g is the Newtonian constant, and r is the distance from the center of the Earth to the body's location, which is very nearly the radius of the Earth. Setting this equal to ma, setting what equal to it? Why would you do that? The body's mass cancels from both sides of the equation, leaving the acceleration that depends upon g, m, and r. So why wouldn't I just do mv? What do I need acceleration for? The net result is going to be a velocity. The net result is 9.8 meters per second. It's a velocity. It's not an acceleration necessarily. It's just a velocity. That will be your velocity, the change in your velocity. I don't need to use the word acceleration. All right, AR can be taken as a constant. This particular value of acceleration is typically denoted g. Right, and you've typically denoted it incorrectly. It's 9.8 meters per second of velocity per 1 second. That's how it should be written. All right. If the body is not released from rest, but instead launched upwards or horizontally with net zero velocity, okay, so it's launched with no velocity, then free fall becomes projectile motion. When air resistance is neglected, so they're just talking about throwing something in gravity and the fact that you're going to get two momenta. You have your original velocities momenta and you have your gravitational acceleration as an added momentum. All right. Uniform circular motion. Let's see. I don't know if they do have a v squared here for no good reason. So I don't know exactly what the purpose of that is. Let's see. When a body in uniform circular motion, the force on it changes the direction of its motion, but not its speed. Changes the direction of its motion, but not its speed. Oh, okay, so they're saying things on opposite sides. Okay, I can sort of get that. For the body moving in a circle of radius r at a constant speed v, its acceleration has a magnitude a equals v squared over r. So in doing the r squared, they're doing a v squared. Now, what you can learn from this animation, oh, absolutely nothing really, right? We know that the velocity is going to be twice the velocity of the one on the inside. If it's twice the distance, it looks like it's more than twice the distance, frankly. So it's going to be faster because it's obviously traveling a larger distance. It has a higher velocity. So they really shouldn't say that because they travel the same number of degrees per second doesn't mean they've traveled the same distance per second. All right, so let's not get into all this, circular stuff. It's very important when you get to angular momentum, which we have to get to eventually. All right, so harmonic motion. I don't really think that's a third law thing, but whatever. Objects, so they got another launching shuttle here. Okay, objects with variable mass. So yeah, that's just pointing out that as you're using your fuel, you're getting lighter, so you're easier to push. Let's see. The physicists developed the concept of energy after Newton's time, but obviously Newton called momentum energy. So if the word existed, he would have called momentum energy, frankly. He thought of it in terms conceptually. Momentum was energy. All right. but has become an inseparable part of what is considered Newtonian physics. Physics developed the concept of energy after Newton's time. And so they're basically saying, well, we created this silly 1/2 mv squared formula, and now we're going to say that it was Newton's, and it wasn't. So they're saying it's an inseparable part of what Newton considered, of what is considered Newtonian physics. Obviously, it's not Newton's physics. Newton's physics is mv. Newton's physics is not 1/2 mv squared. And that's just an absolute fact. All right. Energy can broadly be classified into kinetic due to a body's motion. So obviously they're both motions. It's just idiotic to sit there and say this kinetic energy is something other than mv. It's made out of mv. It's made out of mass and velocity. You're just doing this silly squaring thing. You're pretending one portion of the two components is somehow especially powerful and the other component is especially weak. Due to a body's motion, the potential due to the body's position relative to others. So this whole, as soon as they get into potential and kinetic, they're confusing two subjects. One where you have energy in some package, like storage, like a flywheel, you've stored energy. It's still there, it's still visible. It's just storage. It's not doing anything. You haven't freed it. Okay, and when you're going to have energy that's transferable, you change its function because you take it out of its circularity and allow it to go straight in some direction, and it's more noticeable as energy, where it's more hidden as energy when it's stuck inside a compressed spring or it's stuck inside some spinning object. All right, thermal energy, the energy carried by heat flow. So we know thermal energy is still just momentum. It's just momentum. You're losing momentum to the fact that you've now moved a bunch of little tiny parts of the atoms, and that's the heat. Heat is just moving little bits of an atom. So again, it's just wrong to sit there and imply that heat is not momentum. That's momentum. It's in the energy pool. The type of kinetic energy, like now they have a type, is a type of kinetic energy. No, it's a type of momentum. Not associated with the microscopic motion of objects, but instead with the movement of atoms and molecules of which they are made. So we're just talking about motion. Motion is just the velocity part, and the only other component is mass. And again, the whole distinction is Newton thought mv was more than enough. It explained everything. You don't need to half anything, and you don't need to square anything. So all those little extra bits of crap they plowed onto mv, Newton would say was wrong. It wasn't what he observed. If he had observed it, he would have stated it. If he thought it needed 4 times the force to move something twice as fast, that's what he would have said. But he didn't say that. So again, it's all a canard. Let's see. According to the work-energy theorem, which again has nothing to do with Newton. All right, let's see what that says, actually. I have to get rid of this other thing to see that one. That might be a good one to look up because that's the real overt nonsense. In physics, work is the energy transferred to or from an object via the application of force along a displacement. So again, this is where they're talking about how somehow it's force over distance rather than force over time. Which is, again, just completely wrong. It's always about the time. It's about how fast he throws the damn ball. It's how fast he moves his arm, how fast, that's the only thing that's going to decide. Distance, who cares? Doesn't matter. The distance isn't going to throw the ball faster. The speed of his arm is going to throw the damn ball faster. In its simplest form, for a constant force aligned with in the direction of a motion, the work equals the product of the force strength and the distance. So it really isn't the force strength and the distance, it's the force and the time. But anyway. When a force acts upon a body while the body moves along a line of force, the force does work upon the body. So again, we're just saying that movement and mass causes movement of mass. All right? So if something's moving and it has mass, it will transfer that if it bangs into something. That's when it does work. Work is just transferring energy. So when you heat something, you're transferring energy. You're transferring momentum. And the amount of work done is equal to the change in the body's kinetic energy. So again, absolute nonsense, all right, because we know that the ballistic pendulum takes every single bit of the bullet's, almost all of its kinetic energy. 99.94% of the bullet's energy disappears in the ballistic pendulum, and yet you conserve 100 almost % of the momentum. So you have 99% of the momentum, and you have and you have what would the percentage be? You have 0.001% or 4% of the kinetic energy. In many cases of interest, the net work done by a force when a body moves in a closed loop, starting at a point, moving along some trajectory, and returning to the initial point, so they're just talking again about angular momentum, is zero. So I don't even know what that means. In many cases of interest, the net work done by a force. So they're kind of implying that somehow it's not work when something's spinning. And that's only true if there's zero or negligible friction. But whatever. Is zero. If this is the case, then the force can be written in terms of a gradient of the function called a scalar potential. Okay, so we gotta read this nonsense. In mathematical physics, so it's not in anything real. It's not in real physics or conceptual physics. It's just in Gremlin physics. So you might as well just call this Gremlin potential. Simply stated, describes a situation where the difference in the potential energy, so we know the potential isn't in the thing. The boat sitting next to the river does not have any potential energy. Okay, just doesn't. Of an object in two different positions depends only on the positions, not upon the path taken by the object traveling from one point to another, I guess they're saying. So again, it's just wrong. Okay, you have to travel distance in a line, and if you don't travel it in a straight line, you're going to do more work. So then it says, this is true for many forces, including gravity, okay, but not for friction. Indeed, almost any problem in mechanics textbooks that does not involve friction can be expressed in this way. So we know that gravity is a constant force, and they're just pretty much admitting that friction isn't. The fact that the force can be written in this way can be understood from conservation of energy, so they have no clue. Without friction to dissipate the body energy to heat. Now, friction takes your energy. It's that simple. You will run out of force if you have a friction loss. So if I roll a ball, the ball stops for no other reason, essentially, than the friction with the ground. The ground gets hot, it absorbs all the energy from the ball, and that's it. Momentum goes from being in the ball to being in the ground. Not complicated at all. The body's energy will trade between potential and kinetic forms. So all this potential kinetic bullshit has nothing to do with it. It's kinetic when it's in the ball rolling, and it's kinetic when it's in the damn ground vibrating. They're not anything other than energy moving. Stuff moving. Mass moving. Okay? It's always mass moving, not mass not moving. Okay. While the total amount remains constant. Any gain in kinetic energy which occurs when the net force on the body accelerates it to a higher speed must be accompanied by a loss of potential energy. So just more nonsense about using these silly terms to describe energy in different forms, right? So you're just saying that yes, you can have this energy stored in the gravitational potential of a reservoir, or you can watch the energy squirt out of a hole in the dam, or you can watch the energy bore a hole in a mountain. You know, you can squirt the water at another mountain and make a hole in it. You know, so you can just watch the energy being converted. Energy is always converted, and yes, when it dissipates into heat, it's hard to catch. So if I have one big giant fish, and then I drop the fish in water, and it magically kind of just turns into a million little fish swimming in all kinds of directions, you can sort of understand that the big fish wiggling, I could collect that energy. That movement could mean something. But I can't collect the energy of all the little tiny fish. I can't, tie a string to each one and have them, So I've lost the capacity to use the energy. So heat just means, okay, it's harder to collect heat, okay, because it's spreading all over the place. But, it's hard to get it to point in one direction into a useful piece of energy because it is going both ways and always. But that's it. It's just our inability to capture it in some sort of efficient manner is the limitation. It has nothing to do with the fact that the energy is any weaker. The energy can be applied to something else to create it back into a laser beam, for example. So the net force upon a body is determined by the manner in which the potential energy decreases. So again, it's just silly. You're just exchanging. You're not decreasing energy ever. You're just converting it. And again, gravity is just a stream. It's like the Mississippi River. It's flowing. You can stick things into it and you can watch them moved by the stream. Gravity is an active force, actively imposing momentum. All right. So we'll call that enough. I won't bother getting into rotation and all this other stuff. So anyway, they really did the way they wrote this, right? Because they did the third law and then they never really stopped the third law, and they just kept talking as if this is all applying to just the third law and not the other two laws. So, sort of making a mess out of it, in my opinion. All right, so anyway, they ought to talk about all the other physics and then say, well, look, the first law applies in this circumstance, the second in this one, the second, third, and, they all apply in this circumstance. But they didn't really do that. All right, till the next time and such, we'll call this a video. And, we'll see. Lots of related subjects that we'll get to, no doubt. So, till the next time and such.